All right, ladies and gentlemen, this is the video on gas law stoichiometry using PV equals nRT. You can get this from reading the book, or if you feel more comfortable watching Mrs. Julian, or I should say listening to Mrs. Julian talk about this, then this video is for you. So this is the gas stoichiometry section of the gases note packet. Gas stoichiometry. How does the ideal gas law relate to stoichiometry? Because PV equals nRT, the ideal gas law has moles. That's why it relates to stoichiometry. Stoichiometry is where we use coefficients to turn moles of one thing into moles of something else. Well, moles from PV equals nRT, because we can calculate moles from PV equals nRT, we can use that as what I call a gateway to stoichiometry. Because first step, PV equals nRT, calculate n. Second step, now that you have moles, now use those coefficients to turn moles of one thing into moles of something else. This is how PV equals nRT relates to stoichiometry. Basically, anything in chemistry that allows you to calculate moles is a gateway to stoichiometry. Because PV equals nRT has that n unit in it. Use pressure, use volume, use temperature to calculate moles of a gas. Use moles of a gas to figure out moles of something else, anything else in a balanced equation, and then you can answer the problem. The reverse works as well, and this is what the point is, the third bullet point right here. You can use PV equals nRT instead of using it at the beginning of a stoichiometry problem. You can use it at the end of a stoichiometry problem. Meaning, if you have mass of something and it says what's the volume of gas that you get from 10 grams of this, then you start by doing a regular stoichiometry problem, turn grams into moles, turn moles of the thing that you already know about to the moles of the thing that you're interested in. And then you can use PV equals nRT at the finale to turn moles that you've calculated through stoichiometry, through looking at the coefficients, into pressure. You can turn those moles into pressure, you can turn those moles into volume, you can turn those moles into temperature. So before, at the beginning of the year, when I was saying over and over again, if I give you grams, I've really given you moles. And once you have moles, you can do lots of stuff with it. Now I'm saying with PV equals nRT, if I give you pressure, volume, and temperature, I have really given you moles. Just like with molarity, if I give you, if you know molarity and you know volume, you really know moles. Now with PV equals nRT, if you know pressure, volume, and temperature, you really know moles, because that's all you need to get to sort of kickstart these calculations. So sample problems. We're going to go through 2 sample problems. The first one says, what is the volume, this is a new note packet, what is the volume of carbon dioxide produced at 37 degrees Celsius and 1 atmosphere when 5.6 grams of glucose are used up when glucose is combusted? The first step, we need to write a balanced equation. Why do we need to write a balanced equation? We need those coefficients. You need to know the molar ratio between the compounds in this chemical reaction. So this is combustion. So that means that we're adding oxygen, and we've got glucose that is being combusted, so that's C6H12O6, and then we are combusting it, which means adding O2. And combustion, when we combust something that is organic, carbon-based, we produce carbon dioxide and water, but it's not balanced. So balancing it out, we need 6 carbons on each side. We need 12 hydrogens on each side. So balancing out the oxygens, then I would put a 6 in front of that O2. So I've got the balanced equation. Again, and this is necessary because we're starting with glucose. So I need to know from this balanced equation that the glucose is relating to, and then what is it asking me about? It's asking about the CO2. It's relating to the CO2 by a ratio of 1 to 6. So 1 mole of glucose produces 6 moles of carbon dioxide. That's what the balanced equation tells you. B, road map the calculation, meaning think before you start. Look at the numbers in the problem, think about how we're going to get from the information that's been provided to the answer. So there's a lot of numbers in this problem. Let's kind of start to pull them apart. First of all, it says, what is the volume of CO2? So that means that I'm looking for the CO2. I'm looking for the volume of the CO2, and that's important. That's important to realize that this is what we're working for. And then it says 37 degrees Celsius, so that I know that that's my T. And 1 atmosphere, just writing it up here, that's my pressure. 5.6 grams of glucose. Okay, so 5.6 grams of this are used up when glucose is combusted. So the problem gave me temperature, the problem gave me pressure, the problem gave me grams of glucose, and the problem is asking me for volume of carbon dioxide. You never, ever start your calculations with about the compound that the problem is ultimately asking you about. Meaning in this case, we don't start our calculations with the carbon dioxide because we clearly don't know enough about the carbon dioxide if it's asking about the volume of the carbon dioxide. Instead, we're going to start here. We're going to start with the grams of glucose. We're going to turn grams of glucose into moles of glucose because that's our gut check reaction in chemistry class, right? That's gut check. You see grams, you turn it into moles because we know the formula for glucose, and we're going to do this using gram formula mass, right? Gram formula mass lets you turn grams into moles. So we're not starting with the CO2 because the problem's asking about the CO2. Instead, we're starting with the other thing. We're starting with the glucose. We know more about the glucose. Knowing the mass of the glucose is more specific information than we must be than the CO2. We're missing something about the CO2. Once we have moles of glucose, this is the stoichiometry part, we can use this to get moles of CO2 using the coefficients in the balanced chemical equation, right? You know moles of one thing in chemistry, you can, and if you have a balanced equation, you automatically know moles of anything else that's in that balanced equation. That's the stoich part. And then once we have moles of CO2, well, that's very nice. I'm glad that we have, at this point, road mapped through to moles of CO2. But what we really want up here, what is the volume of CO2? Well, that's going to be a one-step thing as well. We can turn that into volume of CO2. How do we turn moles of CO2 into volume of CO2? PV equals nRT. Because we have pressure, we have temperature, we will have calculated moles, so then the missing variable, remember R is a constant, the missing variable is simply the volume, and we can solve for that. So this is our roadmap of how we're going to do this problem. I'm going to erase the roadmap now just because I need the board space. But now we're going to actually calculate it. So we've thought about the problem, thought about the numbers that are in it. Now we can actually start doing some calculations. So based on our roadmap, we said the first thing that we're going to do is turn grams of glucose into moles of glucose. So, okay, dimensional analysis. C6H12O6. Again, I would, as you're watching this, I would make sure that you are actually calculating gram formula mass along the way. Glucose, C6H12O6, carbon 12, hydrogen 1, oxygen 16. Add it up, you should get 180 grams, 1 mole, C6H12O6. This is our first part of our roadmap. Turn grams of glucose into moles of glucose. Done. You've done that. You've used gram formula mass. Now we have moles of glucose, but we're not interested in glucose. We're interested in carbon dioxide. So now we are going to use the coefficients. Now we're going to say for every 1 mole of glucose, we create 6 moles of CO2. And then that gets us, let's see, grams of glucose have canceled, moles of glucose have canceled. We're left with moles of carbon dioxide. We do that math out, right? If you just take time to calculate, make sure you're getting the same answer that I am. I get 0.187 moles of CO2. We've taken care of the first two parts of this problem by doing this dimensional analysis. We now have moles of the carbon dioxide, but the problem isn't asking about moles of carbon dioxide. The problem is asking about the volume of CO2. So we're going to go to that third part, and we're going to use PV equals nRT. We know the pressure, we know the temperature, and now we know moles. This value right here, this is N. So now we're going to go to PV equals nRT, pressure, and we're going to solve for volume. Pressure is 1 atmosphere. Volume, that's what we're looking for. This is going to stay as V. Moles of CO2, we just figured that out. 0.187 moles of CO2. Figured that out using the glucose, using the coefficients. And then R, that's a constant, 0.0821 liter atmospheres per mole Kelvin. Temperature, remember, convert this 37, add 273 to that. You have to convert, your temperature always has to be in Kelvin. So 37 plus 273, make sure you do this too. I get 310 Kelvin, hopefully you do as well. And then it's just solving. You have one unknown, you know the rest of the numbers, solve it out, we get a volume, I get a volume of 4.76 liters of CO2. So this is a gas law stoichiometry problem where they give you information about one compound, ask you information about another compound, and the key is just finding a way to get moles, some way to get moles. In this unit, it's PV equals nRT is a way to get moles, but you can also you still use the same ways to get moles from the past, meaning using grams to calculate moles, or even possibly molarity and volume information to get moles. So next problem. Consider the reaction 2HGO goes to 2Hg plus O2. Sample problem. What mass of mercury 2 oxide is necessary to produce 2.248 liters of oxygen gas at 25 degrees Celsius and 1.5 atmospheres? And what I'd recommend you doing at this point is actually pause the video and try this problem on your own. Really try it on your own first. Take 5 minutes, go through, do this question, and then once you've finished, unpause the video, watch Mrs. Julian go through it, and see if you got the same thing. Or if you're impatient, simply skip to the end and see if you got the same thing. So that's what I would really recommend. At this point, pause and try it on your own, and then come back. So hopefully you've actually done this problem. All right, now we're going to walk through this. So this question, knowing where to start. What mass of mercury 2 oxide? That means that we're not going to start with the mercury 2 oxide. That means that we end at the mercury 2 oxide, but we're not going to start there. We're going to start someplace else. Is necessary to produce 0.248 liters of oxygen gas at 25 degrees Celsius and 1.5 atmospheres. Oh, oxygen gas. Look at all that information we have about the oxygen gas. We have volume, we have temperature, and we have pressure. We have lots of info about the oxygen gas, which means that that's where we're going to start our calculations. So just road mapping this first, I'm going to use the pressure, volume, and temperature of O2 to get moles of O2 using PV equals nRT. Once I have moles of O2, I'm going to turn that into moles of HGO using the coefficients, because that's what coefficients do. Let me turn moles of one thing into moles of something else. And once I have moles of HGO, I'm going to turn that into the mass of HGO using gram formula mass, because that's what gram formula mass lets you do. So this is the roadmap for the problem. I'm starting with the oxygen because I know more about it. I'm not going to start at the mercury 2 oxide because I don't know anything about it. So doing that workout, PV equals nRT. The pressure is 1.5 atmospheres. Just doing it over here, 1.5 atmospheres. The volume, 0.248 liters. Equals N. That's what we're solving for. We want to solve for moles of oxygen. We've got everything else in this problem except for moles of oxygen. R, 0.0821 liter atmospheres per mole Kelvin. Temperature, 25 degrees Celsius. Celsius, we don't want that. Add 273 to that sucker. Get a temperature of 298 Kelvin. That's what we want to plug in right there. No negative temperatures, not in this thing, because I'm going to get negative pressures, negative volume, negative moles. Can't have that. Can't have that. So solve, and again, make sure you've done this on your own. Make sure you're getting the same answer I am. I get a mole value of 0.0152 moles of oxygen. And by the way, if you're getting something crazy different from me and you've done it over and over again and you're fairly certain you're right, take it to me and I'll just recheck my math. So at 0.0152 moles of oxygen, this is that first step done. Now that we have moles of oxygen from PV equals nRT, now we're going to turn moles of oxygen to moles of mercury 2 oxide. So that's just using coefficients. 0.0152 moles of O2. Coefficients, let's see, the coefficient for oxygen is 1. The coefficient for the mercury 2 oxide, which is this thing, is 2. So that gets me to moles of HGO, but that takes care of that. But I can continue my dimensional analysis and turn moles of HGO into mass of HGO, if I just extend my T-chart like that, using the gram formula mass of HGO, right? Not oxygen, because oxygen is canceled. Now I'm left with moles of HGO. So just adding mercury and oxygen together. 1 mole of HGO has a mass of 216.6 grams, and moles of HGO have canceled. Just doing that math out, multiplying everything on the top together, I get a mass of 6.58 grams of HGO. So gas law stoichiometry problems are really, in my opinion, 95% similar to the stoichiometry problems we have already done, because they're using skills that you already have. The only thing that is different this time is that you're going to use PV equals nRT at either the beginning or the end. And I did 2 problems, one where you use it at the beginning, one where you use it at the end on purpose so that you can see how that works. But it's understanding that PV equals nRT is a way for you to calculate moles. And then once you have moles, you can still do the same things with it that we've been doing all year. Turn moles of one thing into moles of something else. So gas law stoichiometry is basically just adding on to the stoich that we're already doing, simply saying that PV equals nRT can be incorporated into this world of stoichiometry. So that is what you need to know about gas law stoichiometry. You need to feel very comfortable doing questions like this. If you have questions, please do not hesitate to ask.